Our third video from chapter 8 is a shorter one. It's going to pick up the ideas of hybridization that were introduced in video 2 and apply them to higher order bonds, our double bonds and our triple bonds, okay, which we can account for in the hybrid orbital model. Okay. So let's start by considering ethene, okay, which is C2H4, where we have a double bond there in the middle between those two carbons. And we need to think about how that double bond forms. From the first video, we talked about the fact that pi bonds, right, which we see in double bonds and triple bonds, can only be formed by the side-by-side overlap of two p orbitals. Okay. So we need to think about the hybridization of everything that's in ethene and then how those p orbitals come together. Okay? And this is what we're looking at for ethene, okay, C2H4. Over here is what we would expect for ethine, C2H2. We'll talk about that in a couple slides. Let's think about how that forms. If I look at C2H4, my ethene, I'm going to jump back a couple slides here. Okay, I can consider either one of these carbon atoms. They're surrounded by three regions of electron density. Okay? A bond here, a bond here, and a bond here. Keeping in mind a double bond just counts as one region of electron density. Okay? And there's no lone pairs on either of the carbons. So three regions of electron density. Remember the trick with adding the superscripts together means that each of those carbons are sp2 hybridized. Okay? And an sp2 hybridization corresponds to something that's trigonal planar in its geometry, because remember, hybridization is what controls the geometry according to VSEPR, valence shell electron pair repulsion theory. So those sp2 hybrid orbitals are what are responsible for forming all of the single bonds and half of the double bond, because remember, you have to form a single bond before you can build on top of that and form a double bond. So the hybrid orbitals are forming the single bond, and the pi bond, remember that a double bond is one sigma bond and one pi bond. That's from video 1. Okay. That pi bond results from the overlap of our 2p orbital, which wasn't part of the hybridization process. It's kind of left over. Okay. So while the hybrid orbitals are sp2 hybridized in trigonal planar, meaning they're all in the same plane, that leftover p orbital is kind of below and above that. Okay, so it's perpendicular, which allows them to overlap in a side-by-side fashion. Okay? And we need them to do that. The orientation is important so that they can achieve maximum orbital overlap in forming the pi bond. So this is what that process looks like. Okay? For carbon, right, if I write out the electron configuration, right, S2P2, hybridize that, and I'm taking 3 orbitals in, meaning I get 3 orbitals out, 3 new sp2 orbitals that are equal in energy, right? And then 1 p orbital that's left over. This is who's responsible for forming the pi bond. These guys form all of the sigma bonds. And that winds up looking, right, here's all the sigma bonds that are shown, the pi bond that's left over. That's how we form ethene. But as I alluded to before, the orientation is important, right? Those pi bonds have to those p orbitals have to overlap one another perfectly to form that pi bond, okay? Which means that a double bond and a triple bond, those things can't rotate. Any single bond can freely rotate because it's the overlap of two spheres, meaning it can turn without sacrificing any electron density in the orbital overlap. Right? But those pi bonds, if they start to turn, then they're no longer overlapping one another perfectly, meaning a double bond restricts rotation. So does a triple bond. Anytime you have a pi bond, that means we're locked into place. The same idea is seen for triple bonds. Okay. Now, triple bonds, we're thinking about something like C2H2. So that's something that would be sp hybridized, meaning we have 2 new hybrid orbitals and 2 leftover unhybridized p orbitals. Okay? both of those p orbitals overlap one another to form a triple bond. So this here is shown in yellow. Those are my new sp hybrid orbitals. Those would form sigma bonds. And what's shown in red and in blue, those are unhybridized p orbitals, which would overlap other p orbitals to form two pi bonds. One sigma bond and two pi bonds means we have a triple bond. So to summarize everything from video 2 and 3, right, we can use hybridization and valence bond theory to describe bond formation well in geometries. Yeah. But what valence bond theory and hybridization doesn't help explain is resonance, okay, which is why we have to use multiple structures to describe one molecule with resonance. It also doesn't talk about the magnetism we alluded to in the first video. Okay, so these phenomena can be explained by molecular orbital theory, which is something that we'll cover in the fourth and final video from chapter 8.